Hi everyone, today I'll walk through BlockFusion from SIGGRAPH 2024. It's a method for generating large 3D scenes. You can keep extending with no fixed boundary, and the way it does that is a latent tree-plane extrapolation. The work is from the University of Tokyo with Tencent XR Vision Labs, SATU, and ANU. I'll cover the motivation, related work, the three-stage method, the experiments, and then the takeaways and limitations. Let's start with why we'd want expandable scene generation at all. Demand for high-quality 3D content is exploding across games, film, and AR/VR, but almost all prior 3D generation targets a single object at a fixed size. What an open-world game actually needs is a scene you can roam through freely with no hard boundary. Today, that's built by hand by artists, which is expensive and slow. So, the goal here is a 3D scene you can expand essentially infinitely. The teaser shows exactly that. The red block is newly generated, extrapolated outward from an existing village, and the bottom row is the diffusion denoising it from t equals 7,000 down to 0. Doing this well hits two hard problems. First, scene level shape is far harder than object level. The shape variance is tens of times larger, and the number of possible object arrangements is basically infinite. So, the distribution is very hard to approximate. Second, when you grow a scene, the boundary between the old and new parts has to transition naturally, consistent both semantically and geometrically. The closest prior work, Text to Room, struggles here. It leans on monocular depth, which distorts geometry, and its perspective camera is occlusion prone, so it can't really go beyond room scale. A quick map of landscape. There are two broad families. The first is 2D lifting. Take 2D image models and lift them into 3D. DreamFusion optimizes a NURF with SDS walls. 0, 1 to 3 and SyncDreamer generate consistent multi-view images. LRM reconstructs 3D from a single image with a transformer. These tend to be slow and suffer from Janus phase and mode averaging blur. The second family is 3D diffusion, working directly on 3D data with 3D supervision, which gives much better geometry, and a popular representation there is the tree-plane plus MLP hybrid field, which is the family BlockFusion belongs to. If tree planes are new, you factorize a 3D volume into three 2D planes, then an MLP decodes the SDF. It's far more compact than a dense 3D grid, which is what makes it tractable. So, why hasn't tree-plane diffusion already solved this? Robin, NFT, and SSD Nerf showed you can diffuse directly on tree planes, but only on low diversity data, aligned faces, or a single shape net category. On the scene side, retrieval methods can only resemble things already in their database. Texture Room accumulates frames from 2D diffusion plus depth, and Stigen and SyncDreamer lean on height map, which caps their scale. BlockFusion's key move on the right is to not diffuse on raw tree planes. Instead, it compresses them with an autoencoder into a latent tree-plane space, which makes scene-level diffusion stable even at high shape diversity, and then stitches blocks together autoregressively for unbound expansion. Here's the whole pipeline at a glance. 3 training stages. Stage 1. Fit each block as a hybrid neural SDF, giving a raw tree plane. Stage 2. compress that raw tree-plane with a VAE into a compact latent tree-plane. Stage 3. Train a DDPM in that latent space, conditions on a 2D layout, and add inference, extrapolate block by block with a sliding window. The next few slides unpack each stage. First, the data. Artist sim meshes are made watertight using Blender voxel remassing. Watertight matters because it gives a clean inside or outside, which is required to learn a continuous neural field. Scenes are then randomly cropped into fixed-size cubic blocks, big enough to hold the main object. Because the crop position is random, object can get cut off, which is exactly why the variance is so much higher than single object datasets. They also crop a 2D layout map per block to use as the diffusion condition. The table lists the 3 datasets, rooms from 3D front, plus artist-designed village and city scenes, which block counts and sizes. Stages 1 and 2 in detail. In Stage 1, shape is an SDF in a hybrid field. The tree-plane carries geometry features and a shared MLP decodes the SDF. They train with SDF, normal, and Agnol losses jointly feed the MLP on 500 blocks and freeze as a generic decoder and use a coarse-to-fine schedule ending at a 3 by 128 squared by 32 row tree-plane. The catch: diffusing directly on that row tree-plane collapses because of redundancy and large shape diversity. So in stage 2, taking a cue from stable diffusion, they compress it with a VAE into a latent space. Loss is mostly the geometry term with a small KL. And crucially, the latent keeps the tree-plane structure. Figure 4 makes the point. NFT and raw diffusion collapse, only latent diffusion gives meaningful shapes. Stage 3 is the diffusion and the extrapolation. For diffusion, they train a DDPM that predicts G0 directly rather than the noise, using a 3D-aware unit. It unfolds the planes, runs convolutions, tokenizes, and uses self-attention so the 3 planes can communicate. The 2D layout is concatenated onto the planes to control arrangement. For extrapolation, inspired by repaint, they place an empty block overlapping an existing one and synchronize denoising using the noised features in the overlap region. Resampling repeated rollbacks improves the consistency of that transition and removes seams. Figures 5 and 6 shows the unit and how the extrapolation decomposes across the 3 2D planes. Onto experiments. Is PyTorch on 308 GPUs for training, though fitting and inferences run on a single GPU. For cost, a single layout conditioned extrapolation is about 6 minutes, and a full large indoor scene takes roughly 3 hours with a parallel strategy. They evaluate on 3 axes: reconstruction with chamfer distance and normal and SDF errors, unconditional generation with MMD coverage and 1 NNA where 50% is easier, and a 48% user study rating perceptual quality and structure completeness in textured and geometry only modes. Here are the headline comparisons. On single block unconditional generation against NFT, BlockFusion improves across the board. Coverage jumps nearly 30% and 1 NNA moves much closer to the EDR 50, while NFT basically fails to produce meaningful shapes. On indoor scenes, in the user study against text to room, The gap is large. Geometry scores rise about 2.5 points. A nice qualitative note: given a prompt like one bed, texture room produces several beds, whereas the layout condition here controls placement precisely. Figure 9 shows texture room on the left with visible distortion, BlockFusion in the middle, and the BlockFusion plus mesh texturing on the right. The ablation confirms where the gains come from. First, latent versus raw. The latent keeps the shape even after a 99.6% reduction, while a plain latent vector at the same radio fails. So, preserving the tree-plane structure is what matters. Second, the resample count are more resampling lowers chamfer distance in the overlap region, converging after about 3, with none, the two blocks just don't match. Third, the layout condition guides placement while leaving fine shape free, so one layout yields varied objects, and a few others. Z0 versus noise prediction performance. Similarly, non-rigid registration cleans the tiny compression seams, and as a function of creativity, it recombines arrangements never seen in training, like a table shaped like 24 or a heart-shaped room. To wrap up, the core contributions are latent tree-plane diffusion, the first method to get high-quality, diverse generation at the scene level, and latent tree-plane extrapolation for natural growth with 2D layout conditioning for precise control. It produces unbounded, large scenes indoors and out. And unlike procedural generation, it learns the distribution from data with no rule coding fully automatically. They even show a Unity open world demo. Limitations: tree-plane resolution can caps fine detail like tail legs, which super resolution might fix. The bounding box controls only rough placement, not orientations, so they propose orientation map conditioning, and global texture consistency across a very large scene is still open. That's BlockFusion. Thank you for listening.